Today we are going to be talking about how to change concentrations. So let's take an example. If I had a beaker here, and inside my beaker I had a solution, and let's say that was a sugar solution. Let's say I had 500 milliliters of it, and let's say it was a 1 molar concentrated sugar solution. So in here I have little sugar particles that are dissolved in my solvent of water to 500 milliliters. So if I had this and I just asked you, how could I change the concentration of this? Just think about that for a second. What could you do to change this molarity? To make it go up or to make it go down? Some of you might have thought of adding more sugar. If I add more sugar, then I am adding more solute. And if we take a look at our molarity equation over here, molarity is moles of solute per liters of solution. If I add more solute, then I am adding more moles. That means that my moles are going up. But the volume of my solution is not going to change, so that's going to stay the same. Mathematically, if I increase this, what's going to happen to the molarity? It's going to go up. Okay, so mathematically that proves it, but let's think about it logically as well. So if the molarity went up, we're going to say that it's more concentrated now. I've added more solute. So look over here, I add more solute, same volume, just look at my little picture. Definitely more concentrated, more solute per the amount of solution that I have. Alright, let's take the same situation again. And let's see, did some of you guys think about adding more solvent? So if I add more water, how's that going to change my concentration, or what's it going to do? So let's look at our molarity equation again. So molarity is equal to moles over liters of solution, moles of solute. So in this case, when I'm looking at it, when I add more water to this, so let's say I add more water right there. When I add the more water, I'm going to be changing my volume, and my volume of the solution is going to be going up. But when I added water, I didn't add any moles of solute. I didn't add any moles of sugar. So this is going to stay the same. Mathematically, if I increase my denominator, what's going to happen over here to my molarity? It is going to go down. And so we're going to say that we are now more dilute or less concentrated than we were before. Logically, let's see how this makes sense. I have not increased any of these. Some of them will move into the space, the larger space that I now have of my solution as it mixes up. So if I have the same number of particles in more space in my solution, then it makes sense that it's also going to be more dilute. Let's look at one more situation that not everybody thinks about. In this situation, still going to have 1 molar, 500 milliliters, but this time, let's say I let the beaker sit out, and overnight there's going to be some water that evaporates. So let's say we evaporate some of our solvent, and so some of our water is going to leave. So if some of our water leaves, then some of the solute particles that were up there are now going to be down here. Okay? And so if we look at our molarity over here, you can already tell from our picture, if I had to put more particles down in our smaller space here, you can tell that I'm going to have to get more concentrated. I've lost some of the volume but maintained the same number of moles. So moles is going to stay the same. I did not change anything with the sugar, but my volume is going to go down. If my volume goes down mathematically over here, that means my concentration has to go up, which we already kind of proved when we looked at that picture a few seconds ago. Remember when we were doing our pressure, and we had a situation where we started with one pressure and then the pressure changed and moved to something else. That's kind of like the situation we have going on here. So if I started with a 1 molar solution and I had 500 milliliters of it, but then I evaporate some off, and let's say that 200 milliliters evaporated, so I'm left with only 300 milliliters. What would my new concentration be? And remember when we were doing our pressure and we were trying to figure things out, if something was held constant, if we had a constant, we could use that to help us figure out an equation and derive an equation. Well, we do know about a constant here. So our moles stayed constant in this. So I have the same number of moles in this whole solution as I do in this solution, moles of my solute, because I didn't change that. I only changed my amount of solvent. So we can write an equation now, similar like what we did in our pressure situations, where now if we look at molarity, so molarity is equal to moles over liters, but our moles is staying constant. So let's convert this so we can have moles times liters is going to, molarity times liters is going to be equal to our moles. This, remember, is our constant. So in situation, if I had molarity 1 and volume 1, and if I had situation 2, so this is situation 1 and situation 2, but the moles have to stay constant. You guys see what I'm getting at here? Making my own little equation. These two things must therefore then be equal. So the equation that we're going to derive and we're going to use, instead of using L, we're going to replace it with a V, because that's what we see more consistently. So we're going to do molarity 1 times volume 1 is going to be equal to molarity 2 times volume 2. And volume here it had to be in liters because our molarity is moles per liters, but volume over here can actually be in any units as long as they match from side to side, just like we saw in our combined gas law that we used before. So let's just solve this situation that I kind of have going on here. Let's just see what concentration did I make when this kind of problem fell out here. So my molarity was actually 1.0 molar. I just dropped my significant figure there for a second. I could convert this to liters if I wanted to, but I don't have to. I'm going to solve for my new molarity over here and multiply it by my 300 milliliters over here because we evaporated off, remember, our 200 milliliters in the middle of the night. So if I solve my math, multiply here, divide out by 300, my molarity is going to now be equal to, significant figure-wise, 1.7 molar. Now remember, when we just looked at this situation up here, we said our concentration would have to go up. That since I have less water, I'm going to have more solutes per that less amount of space. And here we just proved it. It did go up, and so that makes sense with what we are working with. Now, we can do this in a lab. Like, we could really do a situation where we do dilutions. And scientists are, chemists are really going to be doing a lot of dilutions, a lot of making their own solutions and using them in a chem lab. Often when you want a solution, if you go to the stockroom shelf, they don't have the concentration you want for the experiment that you are going to be doing. So we are going to have to actually learn how to make our own solutions from solids, as well as if we have a stock solution, how do we dilute it, or how do we change it into what we want. And so this is our dilution equation that we are going to be using as we go through and solve these types of problems. So let's set up a little like pretend lab situation here and kind of see how we would go through and solve that problem. So in my problem, let's say that I was going to be working in a lab where I went to the shelf and all I could find was a stock solution of, let's see, 5.00 molar copper 2 sulfate. So this is my stock solution. This is what I just found on the shelf. But when I look at my lab, it tells me that I need to have 0.500 molar copper 2 sulfate. So this is what I need in order to do my experiment. So now I have to, as a chemist, figure out how the heck am I going to do this? I don't have what I need. Well, this is going to be a dilution. I want to dilute my stock into this. So then the question becomes, how can I use my dilution equation in order to help me accomplish this? Well, I need to know how much of this I am going to take, add water to make this. Now, in my lab, I don't need a lot of this solution, and this stock bottle I have plenty of on the shelf. So I'm going to now go and look for something that we call a volumetric flask and see what sizes I have of that. So let's say I go into the stockroom and I find I have a 100 milliliter volumetric flask. As you learned yesterday, when you're doing molarities, volumetric flasks are really important because they give you exact concentrations. So let's say I found a 100 milliliter volumetric flask. And so then I could use that as my vessel to make my solution. So I'm going to use, what I need to find out is how much of this I need in order to make that side over there. So this is going to be my M1, my V1, my M2, and my V2. So let's set up a little math here and solve. So 5.00 molar times this. Alright, so my volume of the concentrated solution, or the stock solution that I want to get, is going to be 10.0 milliliters. So now, what the heck do I do? Well, we're going to see a video in just a few seconds that's going to show you the step-by-step play. But basically you are going to get 10 milliliters of this really concentrated solution, and then you are going to put it in this 100 milliliter volumetric flask, and then add enough distilled water, therefore diluting it, until it will then have just the concentration of what you desired. So, and that is how we do a basic dilution. Alright, so now you need to see what this really looks like in the lab, and now that we've done all of the math. So what you're going to do is go to our online book, which you guys can get to through SharePoint and links, and then you're going to go to videos, and you're going to go to your chapter 15. It's a dilution video that you're going to watch. Make sure that you do take notes while you are watching that, because you guys are going to do a lab with this. You do need to know how to use the equipment and what to do actually in the lab, not just understand the math.